Hey, this is John Paul, and I'm recording, and this is my video. I'm now going to start. Hey there, I'm John Paul, and I'm going to be talking about information entropy. I'm going to talk first about the guy who created it. I'm going to talk about the history of it. I'm going to go over the formulas, the math of it, and I'm going to talk about the related concepts of entropy and thermodynamics. And then I'm going to cover how information entropy is used, some of the applications of it. So let's start off first with Claude Shannon. Claude Shannon is the creator of information entropy, both the formulas that describe it and also he's the one who chose the word that's used for it. Claude Shannon was born in 1916, and interestingly, he worked at Western Union growing up, which is delivering telegrams, which is a interesting background for someone in information theory and communications theory. He was a mathematician and electrical engineer and also worked in cryptography. His biggest contributions were probably in information, the founding of information theory as a discipline, and also he was involved in a lot of electrical engineering, math and applications as well. Um, During World War II, he worked at Bell Labs on fire control systems, and we're going to talk about that first. But he was also involved with many other important contributions over the years. So let's go back to World War II. In World War II, some of the first computers were used for fire control systems, and this used to be done by hand, but they started using communication systems that were electronic or other and initial computers were used for this. So the problem is you have something you want to shoot at. So for example, an airplane flying through the sky, and you want to track it and then send a signal to a anti-aircraft gun and you have to tell it where the airplane is and basically where to shoot. Um, this is a quote from Claude about Claude Shannon. It says, in a classified report, the authors, Shannon among them, noted that there is an obvious analogy between the problem of smoothing the data to eliminate or reduce the effect of tracking errors and the problem of separating a signal from interfering noise in communication systems. So this sort of shows you the environment where some of these theories came up during World War II. They came up in the context of control systems for shooting down aircraft or planes. Um, so this is Claude Shannon's seminal work on this topic, A Mathematical Theory of Communication. He published this in 1948, right after the war. And this was an unclassified document that was published in the Bell Systems Technical Journal, but a lot of the concepts that were in it were taken from another paper published in 1945 called A Mathematical Theory of Cryptography. Now, that paper was classified and people couldn't get to it, so he was happy to produce this other unclassified document, The Mathematical Theory of Communication. And that's the document where people refer back to now as where information theory was sort of founded. In particular, it's where Shannon introduced the concept of information entropy. And now this is a diagram from that paper, Theory of Communication Theory, and it shows sort of the basic idea that he was talking about. In communication theory, you have an information source, like the spotter. I put this on there. This wasn't actually part of his diagram, but just for context. An information source generates a message which is sent to a transmitter, which encodes that message and sends it some signal over something to get to a receiver who decodes the message and then gives the message to the destination. And he has on here a noise source. That's important to the document, to the paper, but it's not really important to our discussion here about information entropy, so I'm not going to really go into it, but he covers that as well. And you can see a sort of a synthesis also between communications theory and cryptography. So we're going to go into information entropy, but before that, I kind of want to give my background with information and how I think about it, which is probably your way of thinking about it too. And it will give you a point of reference for what information entropy was. Before looking at information entropy, I would think about information in sort of a straightforward way. I think that if I have a coin flip that generates a bit of information, And if I have 100 coin flips, that generates 100 bits of information. Pretty straightforward. And I think about it that way because that's how I would represent the data in programming. If I need a variable that can hold 100 bits of information to store it, or I need a place in the database to store 100 bits of information. And if it's a bias coin, if let's say 90% of it is heads, 90% of the time it's heads, and only 10% is tails, I would still record that information using 100 bits. It's just, I would not think about how often one particular event happens or the other. I would simply store it in the database as 100 bits of information. So maybe this is a naive approach, but I think it's the way most people think about how much information there is. And we'll get to sort of the differences. So this is where we're going to get to Shannon's view. So Shannon uses these formula, and he also assigns names to them. So this formula minus the log base b of the probability, this is what Shannon refers to as information content. He also calls it self-information, surprisal, which I really like, and Shannon information is another term used for it. So let's talk about the formula. So it's minus log base b of the probability. The b can have different values. So the standard values, we could use e if it's log base e of the probability of the event. It's nats. If it's log base 10, it's Hartley's, and log base 2, it's a bit. Shannon actually introduced the term bit in his paper about information entropy, theory of communications. So if it's a log base 2 of the probability of the event, that tells you how many bits of information content are produced by the event. Now, note when we're talking about information content, we're talking about information content for an event. It's not for a distribution. It's if we flip a coin and we see some result, it's for that specific event, or a roll of a dice, or whatever else that happens. It's about that specific event. So let's apply this. Let's say we have the information content for a fair coin toss. So for a fair coin toss, it's 50-50 results either way, right? We could get a heads or a tails. Whatever event we see, it's going to have a 50% chance of occurring. So let's say we get a heads, 50. So the information content is log base 2 of 0.5, the probability, which gives us 1. So this gels well with our intuition about information, but it's the same, 1 bit for a coin toss. And he goes on to say a device with 2 stable positions, such as a relay or a flip-flop circuit, can store one bit of information, and such devices can store n bits. So to get the information content for a series of events, you just add up the events and their probabilities and take the log of the probability. Okay, straightforward. And this is where it gets a little different. So what if it's a bias coin? What if the coin doesn't always produce zero, heads and tails with an even result? That's where things get different. So the information content is the log of the probability, or the minus of the log of the probability. So if we have a coin that generates heads 90% of the time and tails 10% of the time, for the tails flips, the information content is 3.322 bits, whereas for heads, it's 0.152 bits. So the information content is actually different depending on the surprisal of the event. The more unexpected it is, the higher the information content. And this is where it's different from your intuition. You sort of have to let your intuition go, I think. This is information content, and it's not the information you're used to. So let's go on to talk about information entropy, which is the key thing to cover. So information entropy can be defined as the summation over all the states of a distribution of the probability of that state times the log probability of that state. So this is where things are different as well. So we're not talking about specific events, we're talking about a distribution of events. So to think about the coin toss, we're not talking about a particular heads or tails event that we see. We're talking about the distribution of heads and tails, or you can think of it as talking about the coin itself. What's the information entropy of that coin? Because it is essentially, if you keep flipping it, a distribution, right? So we have to look at the distribution. We have to calculate sum across the different states, so in this case heads and tails, of the probability of getting those different states based on the particular coin. And another way of is looking at it as going back to the information content. It's the minus the probability of the particular state times the information content of that state, and that's where information content first comes up. So there's two different ways of formulating it, but it's essentially the same thing. So let's apply this. So if we have the information entropy for a coin toss, it's the sum of the probability for heads times the log probability for heads, plus the probability for tails times the log probability of tails, with the minus sign added. So the probability for both is the same, so it's just adding the same thing twice, right? 0.5 times the log base 2 of 0.5, and that's going to give you 0.5, and then you add them together and you get 1. So this actually sort of matches our intuition that for a fair coin toss, the entropy is going to be 1 bit of information produced by that coin. And this is, again, referring to the distribution or the coin itself. When it produces 1 bit of entropy. The difference is where it's an unfair or biased coin toss. We can see this is where it gets very different. So when the probability is 0.5, we get this maximal value of one bit of entropy, information entropy. But as the coin toss becomes more and more unfair, the probability reaches 1 for either heads or tails, then the entropy of the coin, information entropy, decreases. And it's a symmetric result. So at the point where the probability is 0 for one of the results or 100% for the other, then there's actually no entropy produced by the coin at all. So we can see this is not what your intuition gives you. It's a little bit different. And the way I like to think about it is this is sort of about signal transmission rather than just the signal itself. So if you have a signal which is always generating the same value, then you don't need as much information to transmit it. So maybe information entropy is sort of a measure of the variance of the data you're dealing with, right? So if there's a lot of variance in the data, you need a lot of bits to transmit it. Whereas if the data is redundant or it tends to always have the same value, then you don't need as much data to transmit it, right? And you can also think about it as a measure of compressibility. If the data tends to always have the same value, then you can compress it in such a way that you don't have to transmit as much data over the line, right, or to your database or wherever else. And this is also where you can think, well, if the data always has the heads, you don't even need to send a signal at all, right? There's no necessity to send a signal to say the value's heads because the destination should already know that, right? So there's less information to transmit. Okay, so back to this term. So entropy. I saw entropy first used as a term in the context of thermodynamics and physics. And this is a really interesting passage. I'm going to read it. When Shannon discovered this function, he was faced with the need to name it, for it occurred quite often in the theory of communication he was developing. He considered naming it information, but felt that this word had unfortunate popular interpretations that would interfere with his intended use of it in the new theory. He was inclined towards naming it uncertainty and discussed the matter with the late John von Neumann. Von Neumann suggested that the function ought to be called entropy since it was already in use in some treatises on statistical thermodynamics. Von Neumann, Shannon reports, suggested that there were good reasons for calling the function entropy. It is already in use under that name, he is reported to have said, and besides, it will give you a great edge in debates because nobody really knows what entropy is anyway. So this is where it came from. Shannon called the function entropy and used it as a measure of uncertainty, interchanging the words in his writings without discrimination. And you can see this. I think the important thing from all this is that the formula came first and the name came afterwards. So if you're struggling with what entropy means, I think that's an important thing to do, is to understand that this was a mathematical concept initially, and that the math of it matches the entropy formula that's used from physics and thermodynamics, and so it was given the name. It doesn't necessarily propose that there's analogy to them, but they're analogous formula. So I'm going to cover briefly entropy and thermodynamics just to give you a taste of that so that we understand kind of where that analogy came from. So in physics, there's Ludwig Boltzmann in 1877. He created the current definition of entropy, which is this Sg equals this minus K, which is a constant, times the sum of p sub I times the natural log of p sub I. And here, again, K is a constant, and it's the summation over all the different possible microstates of the probability of that microstate times the natural log of the probability of that microstate. So, I mean, really, this is the same formula, right? We saw the same formula for information entropy. It's just that he was applying the formula over the sum of the microstates in a thermodynamic system, whereas Shannon is applying the same formula over a signal in a distribution generated by by some system like a coin. So it's very much analogous. It's very much analogous, and that explains why it's called entropy. But of course, it also complicates it because nobody understands what entropy means. So it's kind of a. I'm not sure if it helps. And I just point out though that entropy in thermodynamics is often described as a measure of order or disorder, and it is that, but it's also order or disorder in a very particular context. In thermodynamics, it's a measure of energy dispersal, how much energy is available to do work. Whereas I think in Shannon's view, it's very much about some data source and how much variation there is in that data source. So it's a little bit different. Same concept, but different applications. So I think we've covered this pretty well, information entropy and what it is and how you calculate it. Let's go on to talk about some applications of it. So first, one of the applications is information gain. And information gain is often used in the context of decision trees. So with a decision tree, you have to decide how you're going to create your decision tree, what you're going to split on in each of your layers of your decision tree. And to do that, one approach you can do is to calculate the information entropy of where you are at that given point, like say to start with, and then how much information entropy you have after you have made your break, after you've made your split. So for example, let's look at the information entropy for the data that's shown in this diagram, in this chart. So the way you calculate information entropy for decision trees is just by taking a sum over all of your classes of the ratio of that class in your set times the log of the ratio of the class in your set. So this is pretty straightforward. So for example, here we have 5 red and 4 green out of a total set of 9. So your entropy is 5 over 9 times the log of 5 over 9 plus 4 over 9 times the log of 4 over 9, which gives you 0.991. So this would be a starting point, say, for information entropy for your set before you apply your decision trees. So let's say now we have a decision tree and we can split it 2 different ways. The first split 1 on some variable, gives us 3 green and 1 red in one group, and then 4 red and 1 green in the other group. So this is a pretty good split. So you'd expect that the information gained from this would be good if you're using it for deciding how to split, right? Whereas the second group, the data is not nearly as well split. It's still pretty mixed together. So I mean, the information gain in this context is really a measurement of the purity of your sets. You want to have sets that are very pure because that shows that your decision tree hopefully will be able to, when applied to real data, will be able to get you the same kind of purity, a high confidence in the prediction of the model. So looking at the splits, the information entropy of split 1 for the first the top set of data is 1 divided by 4 times log base 2 of 1 divided by 4 plus 3 divided by 4 times log base 2 of 3 divided divided by 4. So you get 0.81, and I'm not going to go through it, but for the second split, 0.71. And then you just take the weighted sum of the information entropy of the two sets to get a weighted information entropy of 0.76. Conversely, going through the same math for the second split, you'll get a weighted sum of the information entropy of 0.987. So since we started with 0.991, with the first split, we got it down to 0.7616. The information gain on the first split is 0.229. So that's pretty good compared to the 0.004 we get from the second split. So if we're using an algorithm like this to, for using information gain to decide which split to use, we would use the first split. And that's basically what you do. So if you're looking at decision tree, there is a parameter for criterion where you can choose entropy. If you choose entropy, it's going to use information gain when doing this split. Another application of entropy you'll see is mutual information. Mutual information is the amount of information gained about a random variable or signal from observing another random variable. So this is, for example, if you have a variable that's a class variable and then another variable that's not a class variable, how much information can you gain about the class variable by observing this other non-class variable? And so mutual information is actually very similar to information gain. It's kind of the same formula, but it's just used in a different context. Information gain we just covered is where you're doing decision trees and splitting data sets, whereas mutual information is just in the context of identifying the dependence between variables. And they have analogous formulas as well. Another application of entropy is cross entropy. So this is a concept that comes from communications theory, but it is applied to machine learning as well. In information theory, the cross entropy between two probability distributions, P and Q, over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set if a coding scheme used for the set is optimized for an estimated probability distribution Q rather than the true distribution P. So again, we see the same sort of formula. The cross entropy PQ is the summation across the different classes, in our case, of the probability of the first distribution times the log probability of the second distribution. And where this is used is as a loss function. So when you're trying to optimize your models. So with cross entropy, you calculate this based on with machine learning, where let's say you have several different classes, class A, B, C. You're trying to do the cross entropy between your true label and your predicted label, and you calculate it simply by summing the true label's probability times the predicted label's actual probability that you're predicting. So for example, here we see that most of the data is going to be class B, but we're misclassifying a lot of it as class A and class C. So our cross entropy is 0.977, and we can improve things. Let's say we improve things and we get predicted label is the correct label is being identified 90% of the time, and the incorrect label is only 5% of the time. We can see that the cross entropy is reduced to 0.223. So estimating the cross entropy leads to maximizing the maximum likelihood. And this cross entropy is also referred to as log loss. So if you look at the log loss in sklearn, you can see it's also referred to as cross entropy, and that's what it's referring to. And the last application that I'm going to cover for entropy is in cryptography. So with cryptography, you often have a signal and you want to measure how much randomness is in that signal. And the idea is that you want to maximize the amount of randomness. If your signal has some lack of randomness, then maybe if you're able to predict something, then you can improve your cryptographic approaches to figure out what the actual transmission means. And so just measuring signals can be done with entropy to see how much entropy they contain. And that extends to generating random values, and this is really where it's used in cryptography. So if you are doing some random if you're doing some encryption, you often need a key or a nonce or an initialization vector. You would generate those keys or those values and then share them with your destination. When you generate those keys, you want to make sure that they're random because you don't want anyone to guess what their value is, right? So you need some random number generator. Often these random number generators are based on entropy, and by entropy, it's some random signal. For example, the mouse could be used, the keyboard could be used, the IDE timing sets, air turbulence could also be used. Any of these could be used to generate some random signal, which is then fed to the random key generator. When you're using these actual sort of acoustic random signals, they're called a true random number generator, and you can actually measure the entropy of these sources. You want a very high entropy if you're generating, for example, lots of keys. And there we go. We have covered information entropy and sort of the history and the math of it, and I appreciate your time. Thank you.